All right, guys, here we go with the 1-3 video. It talks about real numbers and the number line. This one's got a little bit of meat to it. So if you want to do a little bit of it, then come back to do some more of it. But in any event, here we go. So after this lesson, I got two objectives. The first one is I want to be able to classify, graph, and compare real numbers. And then I want to be able to find and estimate square roots. All right, so let's take a look. So here's our getting ready, solve it problem. If the pattern continues, which will be the first figure to contain more than 200 units? So what I see here is that in figure number 1, this has 1 unit. In figure number 2, I count 1, 2, 3, 4 units. In figure 3, I count 9 units. And in figure 4, I count 16 units. So your task is to figure out which one would be the first figure to have more than 200 units in it. So I'm going to leave that up to you. So make sure you pause, go ahead and answer. So there's not a lot of room on your paper, so if you need a separate piece of paper or something like that, make sure you explain your reasoning, and then perhaps a table or a rule would help us with that. All right, so go ahead and pause it, give that a shot, and then when you're ready, come on back, we'll take a look at that tomorrow. In the diagrams in the solve it model, the problem we just looked at, what happens when you multiply a number by itself to form a product? When you do this, the original number is called the square root of the product. Okay? So I multiply a number by itself to form the product. When I do this, the original number is called the square root of the product. So if I were to look back here, 3 times 3 is 9. The square root of 9 is that original 3. 4 times 4 is 16. The square root of 16 is that original number 4. So that's what we're talking about there. All right, one of our key concepts is that idea of square root. A number A is a square root of a number B if A squared equals B. All right, for example, 7 squared is 49. So 7 is the square root of 49. 7 times 7 makes 49. So 7 is the square root of 49. So one of our essential understandings here for section 1.3 is I can use the definition above to find exact square roots of non-negative numbers, and I can approximate the square roots of other non-negative numbers. So notice I get this non-negative in here, so I have to be positive or 0. That's basically what non-negative means. All right, let's move forward. A radical symbol, many of you have seen this before, is a square root symbol, but in general it's called a radical symbol. Indicates, looks like that, indicates a non-negative square root, also called the principal square root. The expression under the radical symbol is called the radicand. So if I look at the little symbol here, that thing right there, we call that the radical symbol. In this case, it's a square root symbol. In general, we just call it a radical symbol. And that number underneath is called the radicand. So just a little bit of vocab for you. Here we go forward. So what is the simplified form of each expression? So remember, simplified, as we talked about the last time, is just getting it as small as you can. Get it as simple as you can. So the square root of 81, there's your radicand right there. What number times itself is 81? Well, 9, because 9 times 9 is 81, or 9 squared is 81. So 9 is the square root of 81. So they're asking me what number times itself, that's what that square root symbol means, is 81, and obviously 9. Over here I got a little bit of a fraction. So it gets a little tougher, but really it's asking me what times itself would get me 9 over 16. And the answer would be 3 over 4. Because 3 over 4 squared, which is the same as 3 over 4 times itself, 3 over 4 times 3 over 4, would get me 9 over 16. Because remember, when you multiply fractions, you go across the top and go across the bottom. So 3 over 4 is the square root of 9 over 16. All right, we got a couple try it here's on the bottom. I got it here's on the bottom. So go ahead and give those a shot, pause it, and try them up. All right, now that you're back, the square of an integer, positive or negative whole number, is called a perfect square. All right, so when I take a number and I square it, it's called a perfect square. For example, 49 is the perfect square because 7 squared is 49. When the radicand is not a perfect square, you can estimate the square root of the radicand. Okay, so if I had 49 and I took the square root of it, I would get 7. All right, 49 is a perfect square. All right, so I can estimate whenever I'm trying to find the square root of something that's not a perfect square. So here we go with a little practical application to that. Maybe this will kind of clear it up for you. So lobster eyes are made up of tiny square regions. Under a microscope, the surface of the eye looks like graph paper. A scientist measures the area of one of the squares to be 386 square microns, just a unit of measure. What is the approximate side length of the square to the nearest micron? So here's a cool picture included in your book. So here's the eye of the lobster, all right? And you can see it's made up of these small, almost like solar panel looking things, all these little squares, all right? And they're telling you that the area of one of those squares is 386 square microns, and my job is to figure out how long one of the sides is. Well, the area of a square is the side times itself, the side squared. They told me the area of that one of those little squares was 386. So really, the question is, what number times itself, what number squared is 386? So in other words, what is the square root of 386? So there's two ways I can do it. One of them would be to estimate the square root of 386 by finding two of the closest perfect squares. So if I compile a list of perfect squares, 17 squared, 17 times 17 is 289. 18 times 18, 324. 19 times 19, 361. 20 times 20, 400. Well, it's easy to see that 386 would fall in between there. Okay? So the two closest perfect squares to 386 are 361 and 400. And since 386 is closer to 400, well then, the square root of 386 is going to be closer to 20 than it is to 19. So approximately, that's what that little wavy equal sign means, the square root of 386 is approximately 20. Okay? So it asks me to approximate the side length. Another thing you can do is use your calculator. So on your calculator, there's a square root button. It's normally located by the squared button, the little X with the little 2 over the top of it. So it's somewhere on there. So go ahead and take a second and find that, the square root of 386. And all you have to do, literally, is punch it in your calculator, square root 386, and you come up with a decimal number. Now this decimal would go on forever and ever and ever. Okay? But we could just round it off. So it's about, approximately, 19.6. Okay, so two ways to do it. Find the closest perfect squares, or just use your calculator and estimate. Should be able to do both ways. All right. Our second little part to this lesson is classifying numbers. So numbers can be classified by their characteristics. Some types of numbers can be represented on the number line. All right, so let's take a look. So we classify numbers using sets. And a set is a well-defined collection of objects. Each object in that set is called an element of the set. A subset of a set consists of elements from the given set. You can list the elements of a set within braces. Okay, so just a little vocab here to get us going so we're all speaking the same language. All right, and maybe that'll come, we'll come back to some of those words here in a second. Rational numbers. A rational number is any number that can be written in the form a over b, where a and b are integers, and b is not 0. Because remember, you can't have a 0 on the bottom of a fraction. All right? So these can be any positive or negative number, -5 and -2, 6 and -3, whatever. But this just can't be 0. A rational number in decimal form is either terminating, so it stops, like 5.45, stopped. Or a repeating decimal, such as 0.4166666666, which we could write with a little bar over top of the repeating part, bar over top of the 6. Okay, so it's rational, either the decimal is going to stop or the decimal is going to repeat. All right? Each graph below shows a subset of the rational numbers on the number line. Okay, so as we classify these numbers, a couple things to remember. So natural numbers, those are the numbers that you grew up starting to count with. 1, 2, 3, 4, right? Whole numbers are all the rational numbers, the natural numbers, and add 0 in there. All right, so I grew up, I started counting 1, 2, 3, 4. Those are my natural numbers. I add a 0 in there, and those are the whole numbers. And then once I start putting in the negatives of those numbers also, then I get what we call the integers. So 1 and -1, 2 and -2. All right? So natural numbers are contained within this set. The whole numbers are contained within this set. So the natural numbers are a subset of the whole numbers. The whole numbers are a subset of the integers. Okay? Now we got irrational numbers. An irrational number cannot be written as the quotient of two integers. In decimal form, irrational numbers do not terminate or repeat. So these are your decimals that go on forever with no repeating to it. So 0.10, 100, 10001. So it definitely has a pattern to it, but there's no repeating going on to it. Or you could get a Fabens number like pi, 3.14159, blah, 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 and it just goes on forever and ever and ever. All right? So some square roots are rational numbers, and some square roots are irrational numbers. So a whole number is a perfect square. If the whole number is a perfect square, its square root is going to be rational. For instance, the square root of 4 is just 2, because 2 times 2 is 4. That's a rational number. The square root of 25 is 5, because 5 times 5 is 25. That's a rational number. So if the whole number is a perfect square, then his square root is going to be a rational number. All right? If a whole number is not a perfect square, then his square root is going to be an irrational number. For instance, the square root of 3. Well, if you use your calculator, or you try to think of the square root of 3, you're going to get a decimal that goes on forever and ever and ever and ever and ever. All right? If you do the square root of 10, what number times itself gets you 10? Well, you'd get this decimal that goes on forever and ever and ever. These are irrational numbers. No repeating or terminating decimals. They go on forever. And then when I take all of these numbers, rational numbers and irrational numbers, they make up the big set called real numbers. All right, so let's look at how this all kind of fits together. So I have a nice little table on your note sheet. So let's start with the smallest group. So I grew up, and when I first started counting, those were my natural numbers. 1, 2, 3, 4, 5. These are just some different forms of them, right? Square root of 25 is just 5. 4 over 2 is just 2. All right, so there's just some funky forms of natural numbers. All right, notice that's the smallest box. It's the most specialized set of numbers. Well, then I can add a 0 in and I get whole numbers. So notice natural numbers are contained within the whole number box. So any whole numbers could also be counted as natural numbers. All right, so all of these natural numbers are also whole numbers. But 0 is only a whole number. He's not a natural. All right? Let's keep going. Within that world, now I have integers, which includes all of these, and then some other ones like negatives. So 3 is a natural number. He's also a whole number. He's also an integer. But I get a couple more numbers like negative numbers to get into that set also when I talk integers. 0, not a natural, but a whole number and an integer. So as I work out, the smaller boxes are contained within the bigger boxes. This is a subset of the whole numbers. Whole numbers are a subset of the integers. As we keep working out, now I got my rational numbers. So I get all of my integers, I get all of my whole numbers, I get all of my natural numbers, and then I get some other numbers. Decimals that repeat, decimals that terminate, okay, and all of these guys from before. Aside from those numbers, I get this set over here of irrational numbers, okay? These are not a subset of any of these. So please understand, this is its own little thing. These are the strange numbers that keep going on your calculator and they never stop and they never repeat. All right, if I take all of this group and I put it together, that's called real numbers. So on your paper, please make sure that there's a definite distinction that this box of irrational numbers is not included in those. So I probably should have made a better picture and had a definite dividing line between those irrational numbers and all of these other kinds of numbers. When I put them all together, then I get real numbers. All right? So we're going to come back to that picture a bunch as we answer these questions. So here in problem 3, to which subsets of the real numbers does each number belong? So if I look at 15, all right, and I go back to my diagram. Well, 15, he's a normal number, right? When I started counting 1, 2, 3, 4, all the way up to 15, he's a natural occurring number. He is also included into a whole number because these are included in these. Notice they're also a subset of the integers. Those are also a subset of this bigger box, rational numbers. And all of these are contained inside the real numbers. So between natural, whole, integer, rational, and real, all of those contain the 15. They are not irrational. Notice there's a definite distinction here in that irrationals are not included in anything on this left side of the box. So 15, he's a natural, he's a whole, he's an integer, he's a rational. All right? And he would be a real number, but it says to which subsets of the real numbers. All right? So let's look at number 2, letter B. So I got negative 1.4583. Well, when I started counting, I never counted with decimals or even negatives, right? So if we look back at our picture, he's not a natural number. He's not a 1, a 2, or 3. He's not a whole number because those are just these with a 0 included. All right? He's not an integer because it's not a negative 4 or negative 2. So these are all nice, pretty numbers. Notice these are just in disguise. Negative 4, negative 2, okay? He would be one of these numbers because he does stop. He terminates. So if you were to look at this, his decimal is stopped. It isn't going to continue. All right, so he's a terminating decimal. So he is a rational number. He's a kind of real number. He's a rational number. All right, that's the only subset he falls into. Root 57. Well, let's take a look at that. If I take a look at my calculator, root 57 would be some decimal number because 57 is not a perfect square. So that means that root 57 is going to be an irrational number. And the square root of 57, if you use your calculator, is 7.549834435, and it keeps going on forever. And I knew it would keep going on forever because 57 is not a perfect square. So the square root of something that's not a perfect square is an irrational number. So if he's irrational, well, he's none of these other things. He's on the whole right side of the box. So he's an irrational number. All right? 3 over 10. Well, 3 over 10 as a decimal is 0.3. So that's definitely stopped. All right? He's not even a repeating decimal. He's a terminating decimal. So if I look here, he's none of these numbers. He's not a nice, pretty number. He's not a nice, pretty number and 0. He's not a nice, pretty number but positive or negative. So he's over here. He's a decimal that stops. Okay? So he would just be a rational number. All right? Okay, you get to give it a shot. All right? So go ahead, try those up. There's 2 of them. Give those a shot. Pause it if you need to. All right, make sure you use your chart when you do it. All right, I'm going to keep going, and you can come back when you're ready. Last little piece here. An inequality is a mathematical sentence that compares the values of two expressions using an inequality symbol. So perhaps you've seen these symbols before. The top left one is less than. The bottom left one is greater than. Is less than or equal to. Notice the little equal sign on the bottom. All right, and this one is greater than or equal to. So when I compare some numbers, I can use these signs. 3 is less than 5. 10 is greater than 4. All right? -3 is less than or equal to -3. All right? So that's how I use those symbols. I'm sure you've done that before. So now when I get some numbers that are a little funky, the easiest thing to do in my mind is to change them all to the same form. So I would make them all decimals and then compare them. All right? The square root of 17 is this decimal. I just used my calculator. 4.12310, blah, 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 blah. Keeps going on forever. All right? So that's a decimal. 4 1/3 is 4.3333333333. So it keeps going on forever. So if I look, this number is 4.1-ish. This number is 4.3-ish. So this is smaller than this. This would be to the left of this on the number line. So this number is smaller, left of, or less than this number. So my inequality would be the square root of 17 is less than 4 1/3. All right? So if you just change them into decimals, I think it's pretty easy. All right? Your job, try that one on the bottom. I got a root 129, and I got an 11.52. So change that bad boy into a decimal, and let's see what you got. All right, same kind of process here. What is the order of square root of 4, 0.4, -2/3, square root of 2, and -1.5 from least to greatest, so smallest to biggest? All right, I'm going to change every number into a decimal. To me, it's easiest to compare when they're all decimals. So the square root of 4 is just 2. -2/3 is -0.666666666. And the square root of 2 is about 1.41-ish. All right, so now I have them all in terms of decimals. This one's already a decimal, so I don't have to change that one. That one's already a decimal, so I don't have to change that one. And then I'm going to lay them out on the number line. So I know that I got all their decimal numbers. I'm going to graph them onto a number line and then see what I got. So -1.5 as a decimal, -2/3 as a decimal, 0.4 as a decimal, square root of 2, which is 1.41 as a decimal, and then square root of 4 is just 2. So there they are all as points. Now read the problem. It says least to greatest, from left to right. So this would be the smallest, and then as I go to the right, I'm getting bigger. And if I look at my 4 choices here, the smallest one is -1.5. So I got that one or that one. Now look at the next one is -2/3, so it has to be choice C. Okay, so it's easiest if you make them all decimals and then put them on a number line, and then you can go and compare them pretty quickly. All right, here's one for you to try. All right, so if you take a look at your paper there, should be good for you to try. It appears that some of these numbers aren't exactly the way they were on your sheet. So this should be square root of 9. This should be -7/2. And this should be the square root of 5. So look at your paper, and you'll see it's not exactly the same as this. So please use the numbers that are on your paper. All right? So give those a shot. Turn them all into decimals, put them on the number line, and then go from smallest to biggest, least to greatest. Okay? So give that a shot. I'll see you next time. Peace.